Alright, hello everyone. My name is Edward Lee. I am a second-year master's student at the University of Aizu in Fukushima, Japan. And today I'll be presenting my thesis project, which aims to use genetic algorithms to create artificial sound spaces. So in this project, we do this by generating room impulse responses that characterize an artificial room, and then use some existing plugin tile analogies to create some reverberant sounds in real time. So in this presentation, I'll briefly go over some background information as well as my motivation for this project. Then I'll go over the implementation of the genetic algorithm itself, as well as the plugin framework that we are embedding the algorithm into. And finally, I'll go over our methods for evaluating our genetic algorithm, or basically whether or not it produces the impulse responses that we actually want from it. So first, I'll briefly recap what convolution reverb is for those of you who don't know what it is. So first of all, convolution by itself is a pretty common operation in algebra. You can just think of it as like when you multiply two polynomials together, except in this case the only thing you have to worry about are the coefficients of the two polynomials and none of the variables. So here we are essentially multiplying two arrays of numbers together to get another array that is almost as long as the two input arrays combined. More specifically, it says the length of the output vector is the length of the two input vectors summed together minus 1. And now reverberation, or reverb for short, is just an audio effect that basically simulates sound as it is perceived by its surroundings. Like if you play a musical instrument in a small room versus a large concert hall, for instance, the different characteristics of each room will affect how the instrument sounds. You can also think of reverb as kind of like an echo, except reverb is usually on a shorter time scale than an echo. You can't really perceive any distinct reflections or delays that an echo might have. So convolution reverb, therefore, takes two audio signals, which are on a digital level basically just two arrays of numbers at the end of the day, and you convolve them together. Usually the two signals you want to convolve are one, the impulse response of the room you want to simulate, and two, the audio you want to apply the reverberation to. Now usually when you want to get a impulse response of a particular room or space, the most common method would be to record your own impulse response inside the space you want. But a lot of the time this can only be done using professional equipment, and you have to physically travel to the place where you want to record, which could be an impossible barrier for a lot of people. Well, especially now during the crisis that we are in. So what is the goal of my research project? So technically all I'm doing in my project is to develop an audio plugin that not only performs convolution reverb in real time with the impulse responses that it's given, but also generates some new impulse responses that adhere to some given parameters. So there are two things going on here. One, we're using standard acoustics parameters here, meaning that the plugin will be easier to understand and be more accessible to more users who want to use it. And two, if you already know the acoustical characteristics of a particular space you want to simulate, then our plugin can generate an impulse response that will approximate such a space without you having to go and record an impulse response over there. At least that's what we want to achieve. So now I want to briefly talk about what I use to develop the plugin, which in this case is MATLAB. It has a few great toolboxes available in order for us to get a prototype up and running as quickly as possible, which this includes the audio plugin class, as well as some system objects that we need to perform the DSP. And the IDE that MATLAB includes also makes it easy for us to develop the plugin the DSP, and our genetic algorithm all in one place. And the source code can be compiled into some popular plugin formats such as VST or Virtual Studio Technology, or audio units for macOS, for example. So this is the current user interface of the plugin as I have it right now. I don't have time to explain every single parameter in this presentation, but for now I just want to focus on the 4 parameters on the left. So these parameters control the acoustics parameters that we are using in our plugin. So this is the list of parameters that we have right now. So right now we're keeping it fairly simple. All I have is T60 decay time and early decay time. Basically the time for the impulse response to decay 60 decibels and 10 decibels from the initial amplitude. And then CAD clarity, which describes how prominent the early reflections are compared to the late reflections. And base ratio, or warmth, which controls the balance of frequency content in the reverberations. So the basic purpose of these parameters is whatever values we set for these parameters will greatly determine the fitness value of our impulse responses in the genetic algorithm, or how closely do our impulse responses match these particular values. So now we'll address what exactly is going on in our genetic algorithm and what we're doing to get the impulse responses that we want. So first of all, I mentioned before then that time domain impulse responses and audio signals are basically just arrays of real numbers in disguise. So in our genetic algorithm, we have a population of impulse responses where each gene is a real number between 0 and 1. And an array consisting of these genes make up the genome for each individual impulse response. So in the initialization step, we start with an array of white Gaussian noise, and then we apply some basic processing such as gain reduction, exponential decay, bandpass filtering, and so on, with some extra random variables mixed in at every step. So the purpose of all of this in the initialization is to eventually produce something that not only resembles an impulse response, but to produce an impulse response that actually resembles those that are recorded in the real world. So now that we have all of these impulse responses, how do we determine their fitness values? Well, first we calculate the T60 early decay time, clarity, and base ratio values for each impulse response. So in our implementation, we use shoulder curves or energy decay curves to find T60 early decay time and clarity, and then we have the fast Fourier transform to analyze the frequency content of the impulse response and then find the base ratio from there. So then our fitness value, or in our case, a loss value, becomes the sum of the absolute values of the z-scores for each of the 4 parameters. So we use z-scores here because since we have different units for our 4 parameters, seconds for T60 decay time and decibels for clarity and base ratio, for instance. So we wanted a method to standardize the difference between our parameters. So we, in this case, we actually take the expected values of the plugin parameters as the means for each parameter, and then since we want to be the sum as close to 0 as possible. And then we also calculate the standard deviation of the population for each parameter to standardize the differences between the current IR values and the expected IR values. So that's how we keep track of fitness for each impulse response. And so for the genetic operations, since we wanted to reduce computation time as much as possible, since we wanted a real-time implementation, we opted to keep these operations as simple as possible. So for selection, for example, we just have truncation selection, where in this case we opted to replace the bottom 60% of impulse responses with offspring with offspring impulse responses for the next generation. And then with crossover, we opted to produce offspring through a weighted average. So we multiply each parent response by a random weight and then add the two parents together. And of course, we also had to make sure that the weights sum up to 1 as well. And then for mutation, right now we currently have our mutation rate set to 0.001, which is about 1 out of every 1,000 samples. And for each sample that we want to mutate, we want to have a 50% chance of the magnitude of each sample increase or decreasing in value, as well as a 50% chance of changing sign from positive to negative or negative to positive. So we multiply each sample we want to mutate by a random value from the normal distribution to achieve this. So last thing we want to control is how long do we want to allow the genetic algorithm to run before it actually gives us an impulse response. So in the user interface of the plugin, I also had a drop-down menu that allows the user to select a quality setting, quote unquote, that controls some of the remaining parameters of the genetic algorithm, such as how many generations do we want to run, or what should the size of the population be. So you want to abstract all of these parameters away through this quality setting because one, the end user might not understand what a genetic algorithm is, and two, we also wanted to provide users with a way to control how long the genetic algorithm should run before it outputs an impulse response. So we thought this setting would be a useful way to do that. So here's the diagram summarizing the plugin implementation so far. So we have a button that will trigger the genetic algorithm to run using the current values set by the user. And these values are fed into the genetic algorithm, which will eventually produce an impulse response and replace the current impulse responses with the new ones generated by the algorithm. And these impulse responses are convolved with the input audio signal to produce a reverberated signal. So now that we have our implementation, the last thing we wanted to know is how well do our artificial impulse responses actually match the constraints given by the user or the plugin. So right now we have two different methods for evaluating the algorithm. So the first one is rather simple. We run the algorithm many times, and we want to get some information about the impulse responses that it produces, such as what is the average fitness value, how long, what is the average runtime, how close can the fitness value reasonably, how close to 0 can the fitness value reasonably go, etc. And the other method we have is this is based on what you actually hear if you wanted to convolve an convolve an audio signal with one of our impulse responses. So what we did was we took a few real-world impulse responses from the OpenAir database, calculate the T60 early decay time, clarity, and phase ratio values for each one of them, and then with our genetic algorithm, generate a few impulse responses using those same values. And then we convolved all of these impulse responses with a few audio samples and then generated an ABX test where we asked participants can they tell the difference between a real impulse response and an artificial impulse response. Now, unfortunately, as of the recording of this video, I don't have any results from the survey to share with you yet. But for now, I do have a few preliminary results from our objective evaluation to share with you right now. So here we have a few plots showing the distribution of fitness values from impulse responses generated with random settings. So each time the genetic algorithm runs, we pick a random value for T60, early decay time, clarity 1, etc. And this is what we have. So here we have, you can see that the main takeaway from this is that the average fitness value is somewhere in the 20s and 30s, regardless of the quality setting we use. So this is the same as about 5 or 6 standard deviations per parameter. So this is not really exactly ideal at all. This says to me that we can't really just choose whatever values we want to expect and expect good results all the time, which does make sense, which I will explain in just a bit. And here we have the fitness value distribution for fixed settings. So here we took the values from one of the impulse responses from the open air database, and get the parameter values from that, and run the genetic algorithm many times using those settings. And then this is what we have. So the fitness value is still not perfect, but we can see that that on average is much better before. This is around 2.6, 2.7, something like that on low settings, and then decrease, and then slowly decreasing as we increase the quality setting, which what we would expect from the genetic algorithm is what we hope to get. So overall, what we know so far is that not every combination of parameter values will be able to produce feasible results. This makes sense if you think about the relationship between T60 decay time and C80 clarity, for instance. Longer decay times means that there are more later reflections overall that can overpower the early ones. So clarity will tend to decrease as a result. And so this means that trying to generate an impulse response that has a long decay time and a high clarity value would be really difficult to produce, if not impossible. Also, what we noticed when we were generating the ABX test for other participants was that even when we use the same impulse responses for both speech and music, we tend to hear the differences much more easily through music compared to speech, which makes sense given the audible frequency range of speech compared to music is much more narrower in comparison, and which means we tend to hear the differences much more clearly at very high and very low frequencies. Also, this makes sense given that the base ratio parameter only takes into account frequencies in the 125 to 2000 hertz range. So we have no way to control the frequency content outside of this range either. So one possible solution would be to split the impulse response into octave frequency bands, and then calculate the T60 early decay time and clarity of each band separately. But what this would mean is that this would also require that our plugin be more complex, because we would need to add additional parameters to accommodate for every single octave band. So ease of use of the plugin versus control over the impulse response, that was the trade-off that we had to make there in our plugin. Okay, so that's all the time I have for today. I want to thank you for listening. I hope you enjoyed my presentation. So on the screen right now I have the GitHub link if you want to check out the source code, or if you want to download the plugin and actually try it for yourself. So thank you so much.